Assalamualaikum warahmatullahi wabarakatuh and hi. So today we will present our first lab report, that is vectors and scalars. So there is my team member, which is include me, myself, Siti Noshazliana binti Shaharuddin, and also my teammates, there is Zuhaira binti Ahmad and also Muhammad Firdaus bin Muhammad Fakri. So this is our objective. We have three objectives. So the first one is to verify the equilibrium condition of concurrent force using a force table. The second one is to investigate the effect of force direction on resultant vector informations. And the last one is to evaluate experimental error by comparing measure and calculate the result. For our next slide, we have introduction and theory. Physical quantities are classified into two categories, which is scalar and vector. So for the first one is scalar. Scalar quantities are physical quantities that have magnitude only and do not involve direction. This means they are fully described using just a number and a unit. For example, mass, time, temperature, energy, and also distance. For vector quantities are physical quantities that have both magnitude and direction. This means that to fully describe a vector, we must state how large it is and where it is acting. For example, displacement, velocity, acceleration, and also force. So, for the next slide, we have resultant vector and equilibrium condition. The resultant vector is a single vector that represents the combined effect of two or more vectors acting on an object, obtained by adding all the individual vectors. Well, when all the force acting on an object balance each other so that the total or resultant force becomes zero. The condition is known as equilibrium. In this state, the object experiences no acceleration and will remain at rest or continue to move with constant velocity. So next, we have the vector addition method. We have three vector addition methods, which is tip to tail, parallelogram, and component method. For the first one, we have tip to tail. In this method, the tip is known as arrowhead of one vector is placed at the tail that is starting point of the next vector. After all vectors are arranged this way, the resultant vector is drawn from the tail of the first vector to the tip of the last vector. This resultant shows the combined effect or total magnitude and direction of all vectors. The second method we have parallelogram. Parallelogram is a way to add two vectors by placing them tail to tail. Then identical copies of each vector are drawn to form a parallelogram using the two vectors as adjacent sides. The resultant vector is drawn as the diagonal of the parallelogram starting from the common tail point. This diagonal represents the total magnitude and direction of both vectors combined. And the last one, we have component method. The component method adds vectors by resolving each vector into its horizontal x-axis and vertical y-axis component. These components are then added separately along each axis. After summing the x component and y components, the resultant vector is determined using this total. Its magnitude and directions are found using the Pythagorean theorem and trigonometry. So for the next slide, I will present the key equations for the resultant and angle. So basically, we will use this equation while doing our calculations. Okay, so we have the first one. To determine the resultant force is by resolving each vector into its horizontal x and vertical y component. Each force F acting at an angle theta from from the reference axis can be expressed as fx equals to f cos theta and fy equals to f sin theta. So for the next equation, we have the total components in the x axis and y direction are obtained by summing all individual components. The formula we use sigma fs equals to f1x plus f2x plus f3x, and for y we have fy equals to f1y plus f2y plus f3y. So next, the magnitude of the resultant force is then calculated using this formula, and the last one direction angle with respect to the x-axis. We use these equations.
Material experiment. Force table, ring and center pulley, string, white hanger and slotted weight, protector scale, rule of measuring tape. Experiment produced. Force table were set up. String were attached and weight were held. Magnitude and angle were adjusted until equilibrium was reached. Force and angle we record. Result force was calculated and checked. The experiment repeat with different value.
The next slide is the result for table 1. The table shows the force table measurement. This is the first table that we recording. As you can see, for force 1 we put 1.5 magnitude and 60 degree angle. And for the force second we put 2 magnitude and 50-degree angle. If the force has been calculated and will be that for this answers. The next slide shows an example of vector calculation and vector drawings that include the component fs and fy, the resultant magnitude and the vector direction. The fs component is obtained using force cos 10, with fy use force sin 10. In addition, fs and fy added to obtain a sum of 2.044 f1 and 2.834 f2. The sum of the components give a resultant R value equal to 3.49. The direction of the vector is determined using the formula tan plus 1 f1 per fx, resulting in an angle of 54.21 degrees. The following right figures show vector drawings for two forts, respectively at an angle for 60 degrees for f1 and 50 degrees for f2. The next slide is the result for table 2. The table shows the same force table measurement. It's the second table that we're recording. As you can see, for force 1, we put 1.8 magnitude and 60-degree angle. And for the force second, we put 0.8 magnitude and 50-degree angle. If the force has been calculated and will be that different axis. For the next slide, show the same vector calculation and vector drawings that include the component fs and fy, the certain magnitude and the vector direction. The fs component is obtained using force cos 10, while fy use force sin 10. In addition, fs and fy added to obtain a sum of 1.414 F1 and 2.174 F2. The sum of the components give a resultant R value equal to 2.61. The direction of the vector is dependent uses the formula tangent equal tan negative 1 Fy per Fx resulted in an angle of 54.21 degrees. The lower right figures for table 2 also replace the same vector drawing for the two force corresponding to angles of 60 degrees for f1 and 50 degrees for f2 respectively. Okay, the next slide is discussion. In the experiment, the results for table 1 and table 2 were expected to have the same magnitude by opposite division to the balancing force. However, the experimental value of 4.00 and 3.05 will not exactly the same, indicated that the balancing force they actually to oppose the result in order to enable equilibrium of the ride. Several show of the error may have a priori during the experiment, some as a further in the fully that regular that tension in the trains. Inaccurate mass readings and error will read the angle or the force table. This factor could also cause the street to be least tau, leading to least change in the direction of the force. Lastly, a scalar is a quantity that has magnitude only. Some a mass, whereas a vector has both magnitude and direction. In this experiment, the direction of the vectors plays an important role in determining that the fs, fy component and the resultant.
Conclusion: the experiment successfully demonstrates the that vector addition can be used to determine the result force and achieve equilibrium on a force table. The results show that the result and balancing force were equal in magnitude and opposite in direction, supporting the equilibrium condition. Through this experiment, we are able to differentiate clearly between scalar and vector quantity as well as determine the result of two vectors using the force table. Overall, the activity strengthened our understanding of vector representation, vector addition method, and how equilibrium is established in a system of force.